are going to start with network devices. To manage some kind of provider network device, you need a console. And usually, provider-grade hardware like Cisco, they don't have any fancy front ends, so you can go via browser and check it. But you can go to console and write some commands. How it's usually implemented? It's usually implemented or map or hash map from string to some function pointer to callback. And this callback will accept vector of strings. It will be, let's say, another parameters. In case of our create RP, it will be strings with 2 IP addresses. So this will be body for our possible callback. And here comes the problem. In each callback, you need to validate all the parameters before start using them. For example, for each possible callback in your console, you need to first validate if the argument count is correct. Then you need to convert to some actual type your string, validate it. Oh no. Okay, now it's better. And you need to do the same for all parameters, and actual work will be started. How it was done in our project. And now I'm literally telling you the truth. We had one function with 20,000 lines of code. Seriously. But it's not bad. Not this bad yet. We had over 40 magical variables. No one knows what they did. They held some global state. So, and used copy-paste driven development because there is no way to do something. You just see the nearest function which will look like yours in terms of parameters and copy-paste it. And it's the best. Okay, it's far better. Yes, in multiple places it recursively calls itself. And then checks state of these magical variables. And again recursively calls itself until we find necessary callback. I have no idea who wrote this, but still. And the worst part of it, it works. And if it works, no one goes to rewrite it. So copy paste, copy paste, copy paste. And but what do we actually want? We want a normal signature, so we can check parameters, not some vector of strings generic for all possible callbacks. We want automatic arguments count verification, so we don't need to write this boilerplate if arg size equals something, something, something. And also we need to do the same with string argument conversion. We don't want to boilerplate to convert in some strings. We need to do it automatically. And adding a new command should take only one string, like add command, string identifier, and function pointer. So in pseudocode, it will look something like this. We have a function pointer, we have some vector of strings. We validate argument count, we getting it from function signature and check. And then we create a tuple of arguments which function will accept, populate it with converted elements from the vector of strings. So we take a target type from tuple. Again, it's a pseudocode for now. And populate the tuple from variables from the vector of the strings and validate it. So this some kind of generic approach to this problem. We take everything from the function signature and convert it in generic algorithms. And the last part, we just call this function with tuple arguments expanded. But here comes the problem. How do we store different function types in same container? Of course, we can do something like this. So if, close to what we did, but without magical variables. We can do something like this. So we can make a tuple of pairs and iterate through tuple, finding correct function string literal and comparing them. The problem is this is linear complexity algorithm, so we can do better. And we will. Let's make a compile time heterogeneous hash table with constant time lookup. At first, we need to a little bit dive deep into hash table. At first, we need to check what is a hash function. Hash function accepts some literal and calculate some number based on this literal. The quality of hash function determined by the amount of collisions. So same value for different objects calculated. I'm not going to dive deep into the implementation of hash, but we're interested not just in hash, we're interested in compile time hash from the literal. How to make a compile time? This function compile time. In C++17 we can do this, just add const export. And using this function, we actually can do something like this. We can pass result of this cthash function to template parameter if initial string view is const export. So this is correct C++ code. And how hash table itself is made, structured, I mean. We have a bucket list, it's array. I mean usual hash table, like another map in standard C++. And each bucket, each element of this array is a list of pairs. So we have a key value, key value. And how do we find in this hash table anything? First, we need to calculate possible bucket where our value can be stored. For example, we calculate hash from key 3 and take a modulo by bucket count. Bucket count in our case is 5. And for key 3, we probably have a bucket number 4. Then we iterate all over this list and search for our key. In first attempt, we have failed, and in second attempt, we successfully find it. So this completes the theory of hash table. What do we do next? This will be our interface to heterogeneous hash table. We will have some class called HTBL, and we will populate it with hash table entries, which accept two parameters. First is a key, which will be string, and second is anything, basically any object. We shall have function execute for this table. Execute will take key, which we want to find, and functor. Functor will be applied to the value of the key, and this execute will return true if key is found and functor was applied. Otherwise, it will return false. For now, we're going to check a really simple functor, which just will print type ID of the value. And what will be output if we take and execute for key 1, functor will output just int. If we do the same for key 2, it will output std nullptrt. And if we do it for key 3, which is not present, it will output not found. But still, for now, it works. So we can apply same functor to different, absolutely different types. Okay, how it was implemented? First, we are going to store hash table entry, which looks like this. Basically, this is pair of key and value, where key is a string view and value is everything. And we have an additional parameter in a template called hash. This hash will be compile time and not present in any of executable. It will be only used on compilation. And we need to use macro called hash table entry key value because we need to calculate this hash. We don't want to duplicate string literals, and so we will use macro here. And also we need to use decal type for value because C++17 value feature, called argument template deduction from constructor for class is not working when we are supplying our values. And in this case, we supplied hash by ourselves. Okay, so we have a key, we have a value, and we have some compile time hash. Okay, this is what it would like in runtime, but we can do it in compile time like this. So basically, nested tuples of tuples of tuples of tuples. Pros of this implementation: it actually works. Code is beautiful. It's strange when I apply beautiful to heavy templatized code, but still. But it have one pro which discards all the one con which discards all the pros. It will never compile. If I have added like 50 entries in my hash table, in Visual Studio compiler just died immediately, eating all possible RAM from my PC. So let's think what we can do. Basically, we know if we create a hash table with such pairs, I just shortened the writings, and we know that pair 1 from previous slide actually belongs to bucket 1, pair bucket 4, pair 2 to bucket 1, and so on. So these written pairs and their possible buckets. Okay. And what we need to do is we need to calculate element count per bucket. We are going to not to change our arguments, but we are going to generate additional metadata which will look like hash table for us. It will retain constant lookup, but it will be not any way altered. So these pairs will remain the same, no compile time calculations will be performed for them. Okay, we need to calculate element count per bucket. It's 1, 2, 0, 2, 0. How it's done in compile time? We will be using alias hash meta t. It's basically array of integers which will have the same size as tuple we provided. And we will create an array of occurrences, and we will calculate them. How? We just go through the whole tuple which was provided in constructor of hash table recursively. Using if const expr here for recursion is far better than partial template specialization, so C++17. And we are going to recursively call itself, calc occurrences with next index, until if const expr generates nothing, and it will be end of recursion. So what we are doing, we are taking hash from each element of tuple and taking a modulo by buckets count. In our case, it's a variable called SZ. And we increase appropriate index. So we have calculated this array of count, but count is not really relevant in our case because we need to calculate offsets. Offsets will be used for indexing where our virtual bucket in virtual hash table start and end. How to calculate the offsets? We take already calculated occurrences array and basically transform it via following way. So we are taking previous element of the offsets table and previous element for occurrences table. So offset of the first bucket will be 0 always. offset of the second bucket will be 0 plus 1 will be 1. Offset for second element will be 0 plus 2, 1 plus 2 equals 3, and so on. We've calculated those offsets, and we are making copy of them because we will need them later. Second part of the metadata required for virtual hash table is array of indexes. This is the hardest part, even for me to explain. Offsets will point to indexes. So basically, when we want to check if there are any element with some hash, we check the possible bucket number, for example, bucket 1. We check, okay, bucket 1 starts from 1 and goes to 3, like this. B1 is 2 elements. And those indexes shall point to tuple itself. And we need to fill those indexes. So again, we are not touching the tuple itself, so no hardcore compile time calculations were involved. We are just calculating indexes. It is far faster. Okay, how it's done? We see, okay, this is a pair 0. We calculate hash. We know that there is 5 elements in hash table, and we know it is in a bucket 1. We check element 1 of the offsets points to 1. And we see we can put our index 0 to the bucket 1. Okay, next element. Element 1 is in bucket 3. We again see the array of offsets and see it points to third element 3 in the indexes. Again, we put it here and we increase them. In previous slide, we also increase in offsets array, so it looks like index. It looks like current place to insert the next index. Okay, pair 2. It's again bucket 1, but since we already increased the value in the offsets, we put index 2 in the next free place in the bucket 1. And we do the same with pair 3, and we do the same with the pair 4. And our result looks like this. We have the original offsets, and we have indexes table. How do we look up? How do we do a lookup? In case if we want to look up for pair 3, for example, we check in which bucket it belongs. It belongs to bucket 3. We see, okay, third element of offsets is 3. And next element of offsets is 5. So possible places in index array will be 3 or 4. And then we check if element 1 in tuple is what we want to find. If not, check the next element, element 3, and this is what we want to find. Okay, how it looks in code. This generator. Again, we are doing recursive search through the whole tuple of our pairs. But for now, we calculate bucket, taking the hash element and moduling it by tuple size. Then we take a place where in indexes array it would belong by taking it from offsets array. And they simply placing it into indexes, increasing the offsets, and recursively calls itself for next element. That's how it's done. Overall interface of hash table looks like this. So we have a member tuple to which we simply following the forwarding all arguments. We have offsets array, which are calculated on basis of tuple, and we have indexes array, which we just calculated based on tuple and offsets array. And this is all stored in this class, but we have a function execute which accepts key and functor. There is need to talk a little bit why it accepts functor. If we are talking about heterogeneous data types, you just cannot return anything that you want because you need to return one type. And if there is a different types, you can return std any and then use any cast. But this completely defeats the purpose of data structure because you already know what you are taking. Or you can return std variant with all possible types, which can be met in tuple in hash table. But this is another problem. To use this variant, you need to provide functor with all possible overloads. So why bother when we can directly pass this functor here? Okay, I think I already explained this. In function execute, we take from, which is beginning of our virtual bucket, and to, which is the end of our virtual bucket. We have this ternary operator here because if bucket is last possible value in array, we need to forcibly put tuple size n to it instead of next element. And this is the second part of this function. We are going in cycle from to and using function big switch. Why it's called big switch, you will see in the next slide. It's very big. Okay, if big switch found the element and applied functor to it, okay, no problem. If not, and all possible indexes in bucket has been already tried, so return false. The interesting thing here is that we have indexes array, and while we have from and to from offsets array like 1 and 3, big switch takes indexes. So it takes medx1, which will be 0, medx2, which will be 2. So there is this indexes are mapping to tuple is actually working. Okay, big switch problems. We cannot somehow map runtime index to compile time integer to use stdjet. I guess, okay. I forgot to add tuple here, my mistake. Actually, everywhere jet, index, and in parentheses there is a tuple. Basically, it will look like this. Switch index, if 0, get 0, check keys, and apply functor. If 1, get 1, check, apply. If 2, if 3, if 5, if million. And there is a big problem. What happens if our tuple is less size than we have switches available? It will be compile time error because in some case we are trying to use stdjet get on element which is not present in tuple. We can check it in compile time and it will be compile time error. How we can fix it? Okay, ugliness starts now. We can use if context everywhere. But there are another problem. What if the tuple bigger than our available quantity of cases? And there is nothing we can do except static assert. So at least we have a nice compile time error here. But actually this is not a solution, this looks like hell. What to do? If we would have a time machine, we could go to C++23. And this is actual proposal exists from David van der Voort, I think. We have this some kind of text template, which is case something if const text for something less than tuple size and get something dot key and so on. David Wonderwood proposed to do a token stream injection, so we can generate some code based on compile time variables, not textual generation like it's done in macros, but some intelligent thing. So in our case, we can get all the indexes from the 0 to tuple size and inject them into code, inject all those cases, and it will work. Okay, we don't have C++23. And let's go to my favorite slide. Good old John Carmack saw the comment about boost code and had a moment of panic before realizing that it was not C++ boost. I think John worked on a game called Rage, it's his last game on ID Software, but still. We have something like this, and instead of copy-pasting case n something, 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 again, we can use boost. And not the boost, but darkest part of boost, called boost preprocessor. Actually, when we define max switches, we can again static assert that max switches is always bigger than our tuple size. But in case if it's lesser, we can just generate all the stuff using boost preprocessor repeat. What boost preprocessor repeat does? It generates code based on another macro. In our case, it's nvswitch. nvswitch is a macro which contains our this copy paste part actually. And instead of 0, this should be index also. And when boost pp repeat using some kind of black magic compiles, it actually generates case 0, case 1, case 2, case 3, case 4, and so on up until case max switches -1. Actually, I don't think anyone knows how it works, but it works. Okay, this is actually approach. Okay. Later. And the third approach, what we can do here, is we can combine case switch approach with recursive approach. What we can do? We can introduce template variable called back, which equals 0 by default. And then we can do switch using cases with back multiplied by something. So it will look kind of like this. So we are switching between 10 values, and if our index is not in this range, from, for example, in our case, from 0 to 9, we call itself recursively again, but with increased back. And now we are switching between 10 and 19. We can recursively call itself again with increased back, and recursively check again if we from 20 to 29, 30 to 39, 40 to 49. While it's not constant approach, it's also ugly, but at least it compiles every time, no static asserts. But unfortunately, I would stick to C++23. And let's use this Frankenstein child of Alexandrescu for initial idea from the string to function mapping. We have our little hash table, which holds one key and one function pointer. And what functor should we use to first validate the params, so its count equal to function signature arguments? How do we convert and how to execute? First thing first, we need to somehow rip off arguments from the function. How it's done? Actually, we easily can get arguments from the std function, for example. We just match variadic arguments, create tuple, and return it. It will work. But in case of, for example, function pointer, code will be different. If we use, for example, lambda with capture, code will be different. But again, C++17 gives us a nice approach to this, generic one. We can wrap whatever we want in std function, and in C++17 it will work because std function from deduction guides is able to deduct what it is holding from constructor. And previous function will work on all possible functors due to this. Okay, we now see that tup is a tuple of int and float. So we got arguments from the value from the function stored in hash table. Next thing what we can do is generic conversion. Here we already can actually insert some checks about function count arguments and return false if something is wrong, or throw exception. But converter is tricky. We need a function and a lot of full specialization of this function. So we can always call converter and type to which we can convert, and string. And generic approach will return correct value here. But this is not enough. We also need to know what is index sequence in standard library. We can have an alias called make index sequence, which is actual alias to index sequence with compile time number progression. So, and if we call some function with make index sequence 5, for example, we can match in template argument all these index sequences in variadic pack. And if we unpack them using 3 dots, we can actually see that it will be unpacked to 1, 0, 1, 2, till n-1. Why do we need it? Because we can unpack not only index sequences, but we can also unpack, let's say, exteriors of these sequences, like this. For example, we have a tuple with arguments, and we call some helper with same tuple and make index sequence based on size of arguments of the tuple. And if we do get n tuple and only then 3 dots, it will actually be converted to get 0 tuple, get 1 tuple, get, and so on until n-1. So why do we need it? Okay, that's our function converter, which accepts some container with strings, doesn't matter, and the tuple of arguments to which we want to convert. And we return helper with the index sequence of this. And since we know the index sequence, we can use convert and all overloads with tuple element t, which return nth element of the tuple. And as argument, we can pass nth element of the container, and only then put 3 dots to unpack this value, unpack this expression, I mean. And it will be unpacked to something like this. So 0 element of tuple will be converter element 0 to type of 0 element. And basically, if we remove tuple element t, it will look like this. So we actually get a tuple of int and float. And right now, we have converted our elements, our strings 3 and 5.7, for example, to actual int and float. And then we call std_apply, and that's all. So this generic approach actually works on all types of functions, all types of arguments, and there is no boilerplate. You actually can add each new function using only one string, so hash table entry key and function pointer to something, capturing lambda to something, or whatever. And to spice it a bit, nested hash tables. In case of multi-word commands like create IP without underscore but using two different words, we can apply a recursive approach. We are not will be seeking only for functions, but we can craft a functor with overloaded templates, something like this, which will match hash table separately and execute something like this separately, and matching function to everything else. So in our case, it will be function pointer, and we will call the code which was in a few slides ago, this generic code of engine. And I hope you understood what I'm talking about. Code and complete implementation will be here in GitHub once I get home.
Question. Isn't it possible to make a compile time loop? So with this big switch case what you have done, wouldn't it be possible to do a compile time loop?
Yes, of course, you can just iterate recursively through the tuple until you find something. Yeah. Like I did in this example. Let me... Actually, we are doing this here.
Yes.
But the problem is, it will be linear approach, strictly linear.
Of course.
And
it depends how many entries do you have.
It will always be linear approach because
the question is how many. If you just have 50, I think it's not a real time problem.
If it was just 50 entries, we wouldn't have to write this hash table at all. We can just use a tuple of pairs and iterate them linearly. The main idea of this is to make constant lookup somehow in compile time structure which accepting constant time lookups. Yeah.
Okay. Still related to this. Come on. Can exist some kind of wizardry use of the C++17 fold expression to avoid the recursiveness and make the compiler perform it linearly?
If you're talking about removing recursiveness, I don't think it's possible because all these data structures need to be traversed somehow, and you cannot traverse it using some kind of regular indexes. You mean folding expression?
Sorry.
Okay. I don't really think so. I've tried to apply them sometimes, but I have been unsuccessful. But this, I think, folded expression is the hardest feature of C++17, so I don't have enough grip to use it yet.
It works on overloaded function?
The problem is when you trying to get signature from the function. If there is one function, it always works. If there is overloaded function, there is compiler error always. But yes, yeah, you can cast it without problems. But actually, you can use hash table of tuples to functions. Okay, let's not go here. Okay. How long it took to compile 20,000 line of function? Equivalent of this? Actually, a few seconds. Actually, this was a surprise for me because this is much faster than, let's say, rebuilding tuples if we could use, if we can want to mimic original hash table structure. And just as a bonus, not to answer the questions, this actually used in production, but not in hash table variant. It's used as linear tuple lookup.